We're recording now.
Okay.
So
Okay, welcome everybody. Welcome everybody to the first session for today, which will be on MPC, ORAM, and Symmetric crypto. My name is Svetlana and I'll chair the session. And I'm happy to introduce the first speaker today, Karmit Hazai. And I guess she will share now her screen.
Yes.
And she will talk about gradual GRAM and secure computation on RAM programs.
Can you see my screen?
Yes.
All right, great. Hi, everyone. So this is a joint work with my student, Mor Leventhal, and this is about gradual GRAM and secure computation for RAM programs. Okay. So secure multi-party computation is a tool that allows to set of parties to compute, directly communicate without leaking any information about nothing but the output to any of the parties. And the security guarantees is as in the setting with the trusted party. So specifically, any adversary that corrupts a subset of parties cannot learn anything beyond the trusted setting. And we distinguish two types of adversaries, passive and active, where passive is the benign attack model, where the adversary follows the protocol specification, but tries to learn some additional information. And also the corruption model, where an adversary can corrupt either less than half of the parties or n-1 of the parties. And in this paper, in this work, I'm going to focus on the two-party setting with passive security. Amplification to active security can be done using existing tools. And by now, we also know that MPC has many important applications like auction with private bids, privacy-preserving data mining, and so on. Okay, good. So most of the research today, two-party, also in multi-party, has been performed for Boolean circuits, also for arithmetic, but specifically for Boolean circuits. And it doesn't handle efficiently accesses to large memory, which is translated into if you take the memory and translate it into part of the input, this is causes a huge blow up because we need to scan the memory every time we access it. On the other hand, most of the applications today in practice are more efficiently captured using random access memory or RAM programs that allow constant memory access. So also, if we try to translate a RAM program into a circuit, so if the running time of the program is T, then the blow up will be T cube, which is non-scalable even for small memory sizes. So to address these limitations, protocols have been considered, have been designed in the RAM model, okay? And such protocols also additionally support memory accesses. Good. Okay, so in the RAM model, we have a remote CPU that is given an input X and access into to a physical device or memory. And the running time of the program is typically much smaller than the size of the memory, it could be even at the polylogarithmic scale. And the access pattern into the RAM model includes the, if you want to, what kind of data is captured in these accesses, is the memory locations and the data itself. And we know also that these access patterns leak information. So it's not enough to encrypt information or those elements that we want to store in the memory. We also want to hide the actual access pattern. So for that, we have Oblivious RAM, which was introduced by Goldratt and Ostrovsky. And here, this is a tool that supports dynamic memory accesses while preventing any leakage from the memory. Namely, ORAM is a technique for hiding all the information about the memory for a RAM program, including both the content of the memory and the access to it. And the overhead is measured with the blow up of the size of the compiled program or the memory, as well as the number of memory accesses we actually need to do in the compiled program per a single access in the original memory. Okay, so now in secure computation for RAM programs, we have two parties. They have secret inputs and they want to run some program P on their inputs. And they mutually also, while running the program, need to access some memory. So the protocol needs to support also these accesses while running privately the program on their inputs. And without loss of generality, usually when we design such a protocol, we assume that the memory is initialized empty and is occupied on the fly. Okay, so drawbacks of previous approaches. So first of all, since the memory is usually assumed to be empty, there is no reason to initially run the goblet memory algorithm, which is very expensive. Also, passive to active applications are very complicated because we need to make sure this memory garbling algorithm has been done correctly. So either using techniques of zero knowledge or cut and choose or any MPC protocol that ensures this correctness. Finally, all the constructions that we have today, they're built in two phases where some intermediate phase of UMA, unprotected memory accesses, that which means that the memory is not encrypted and the access pattern is leaked, and then they're compiled into full security using ORAMs. Okay, so I don't know how much time do I have, but let me quickly say that GRAM are schemes that are analog to goblet RAMs or goblet circuits for the RAM programs, and they support the same algorithms as well as garbling the memory and the program, as I was saying before. And as I was saying, the input size to the program is small and does not grow with the memory size. That's the main point when you do garbled RAM. And it's important to note that at the heart of every garbling mechanism, there must be some integrity mechanism, even for semi-honest protocols, because we have to ensure that the parties will not roll back to previous instances of the memory. So that makes all these garbled RAM constructions much more complicated. So let me just quickly say our results and end with this. So in this paper we explore we explore the notion of gradual ORAM, which update the memory on the fly. This concept was implicitly used in previous work. And based on this gradual ORAM, we show how to construct or we introduce the concept of gradual RAM or gradual GRAM, sorry, which is basically the extension of GRAM constructions, where in these constructions, the memory is garbled on the fly. There is no memory algorithm at the beginning, which means that it is not as expensive as the original construction. And we also show how to instantiate our concept with the gloss GRAM construction. So very briefly, using this concept has many advantages. We can adopt techniques for Boolean circuits because we can basically translate our construction into a sequence of CPU steps. We don't have anymore this garbled memory algorithm. So we inherit all the advantages we already have and know from Boolean circuits. We can push most of the work to the offline phase, and switching from semi-honest to malicious is much, much simpler in this case. We compare our construction to the gloss construction. Basically, we compare the overall number of steps we require for every CPU step and also the size of the circuit. And we show how to shape a logarithmic factor. And I'm sure there's a lot to be done in this domain because there aren't too many constructions that support GRAM. And our approach actually pushes the way we design such protocols into the domain of Boolean circuits. Thank you very much.
Thank you. You are perfectly on time. I don't have any questions on the question and answer panel. I have no question myself. Anybody from the panelists maybe?
Yeah, I have a quick question. Did you implement this? I am always curious.
Not yet, not we haven't.
I'm always curious how GRAM will behave, and you know, is there something that it will run faster in practice? And, okay.
I mean, it's hard to compare to the functionality. I mean, you have in Boolean circuits, but I'm sure for some functionalities you will be able to do.
Yeah, so yes, for sure. So some functionalities it will be faster because if you need this general control flow, so if you have a program that you can go this branch, and branching and loops, then if you start implementing it using regular garbled circuit, then you're going to be in trouble. And I guess one question is, where is the break-even point? Like how big this program has to be, and how many minutes, days, hours it will run when GRAM overcomes. I think it's a good direction, but I think it'll be good to improve it concretely, and that will be really good. And your work is.
That I agree. I definitely agree. I think it deserves much attention also. I mean, this model, definitely.
Yeah, thank you.
Okay, thank you. And you have a short break now. We have the second paper, which is about efficient protocols for oblivious linear function evaluation from Ring LWE. And I believe the speaker will be Daniel Escudero.
Hello, yeah.
Hello, you're present, so you can start sharing your slides while I read the rest of the co-authors of the paper. So this is a paper joined with Karsten Baum, Daniel Escudero, Alberto Pedroso Ulloa, Peter Shaw, and Juan Ramon Troncoso Pastoriza.
Okay,
you can start your presentation, and we have about 10 minutes for questions and presentation.
Excellent, thank you very much. Just 1 second, I need to hide the video panel, which is quite intrusive. Okay, perfect. I'm done here. So thank you so much. So yeah, this work is about oblivious linear evaluation. And I want to start by saying what oblivious linear evaluation is. So in this primitive, you have two parties. It's a two-party functionality, Alice and Bob. They're going to send some inputs to some to this functionality, and then the functionality is going to return some alpha to Alice, which is completely random, and some beta to Bob that is defined as u times v minus alpha. So this turns products into sums. And maybe you have seen it in some other ways, in some different forms. This is technically random OLE, but in any case, like this is the definition I want to consider because all of them reduce to each other. Okay, so this is a two-party functionality that has many, many applications. Particularly, it has applications to MPC. You can use it to generate triples. You can use it to handle multiplication of secret shared values. It has application to privacy intersection and much more. So it definitely makes sense to focus on this primitive, as improving it means improving many other constructions. Okay, so I'm going to cut right down to the chase. What are we doing in this work? We're presenting a new OLE protocol based on the Ring LWE assumption. And our protocol has this very nice feature that it has like 1/2 rounds of interaction. I'm gonna define what it means in a moment. We have two variants. One is a public key variant, and what I mean by this is that the setup required for this construction to work is only a simple PKI, so no correlation at all, just one PKI on the side of Alice and one PKI on the side of Bob. And then, I mean, like a secret public key pair. And then the communication complexity of this construction is of 2 ring elements per party, so it's actually pretty efficient. And then we have a secret key variant, in which the setup is more correlated. I'm going to explain what the setup is in a moment. But the trade-off of this is that now you're going to communicate only 1 ring element instead of 2. So a more correlated setup, but a better communication complexity. And of course, this is very relative to the setup, to the computer use, to the parameters. But we can state that we can get like a complexity of 2 seconds for an evaluation of 2 million OLEs. So I think this is very competitive, and I invite you to check out the paper for the concrete details and comparisons with other works. But at least I would like to say the sentence of 2 million OLEs in 2 seconds, which I think is pretty good. Okay, so I want to briefly show you how our constructions work. So I invite you please to ignore the notation. I haven't defined what this ORAM is. It's like a polynomial ring, modulo M, but full details are in the video, in the full length video. But I just want to give you the general idea. So you have Alice with a vector of inputs, Bob with a vector of inputs as well. And the first thing that's going to happen is that Bob is going to send certain encryption, which we call key-dependent message encryption, based on the LPR encryption scheme, to Alice, using certain public key that is defined from the public keys that each individual party holds. Now, this is the first message, and the public key encryption is going to include 2 ring elements, or 2 vectors of ring elements to be precise. And they're going to define some local values, like this is just local computation, is some rounding, multiplying some secret keys that they have. And then at this point, you should have already some correlation. In this case, S is going to be some secret key that is derived from the secret key of the parties. The next thing that happens is that Alice will send to Bob another encryption, but now is where the concept of 1/2 rounds kicks in, which is this looks like one round. Bob sends one thing and Alice returns another thing, but the thing I want you to notice is that the message that Alice is sending is completely independent of the message that Bob sent initially. So these 2 things happen simultaneously. I'm going to show a diagram in a moment about how this actually looks like in practice. But the point here is that it's a simultaneous message. So it's not really one round in the sense that Bob sends to Alice and Alice returns to Bob. Okay, they do more local computation. And after this, you can show by checking the parameters correctly that they're going to get like a correct OLE relation. As I said, we can optimize this by using a secret key variant by spending a more complicated setup, which is more like an OLE relation. This is the setup we need. And if you have, you also assume certain access to uniformly random values. And if you have this, you can modify the protocol so that it becomes more efficient. And I'm going to skim over this like very quickly, but I just want to give you the idea that the protocol operates the same. One message on the left from Bob to Alice, then you get like a certain correlation, but this message is just one ring element now, or one vector of ring elements. And then you have one message in the other direction from Alice to Bob. And then they do some local computation just like before. I understand that I'm not giving the intuition about why this works, but I already do that in the full length video. So I invite you to see that. But I just want to give you the idea of the communication pattern and so on. It's exactly the same as before, but with less ring elements. And now you have the correct correlation again, at the expense again of a more complicated setup. Okay, active security is unfortunately not that cheap. So there are many critical points in which that break if you consider an active adversary. Again, I explained them in the full length video. And we do develop some efficient zero knowledge proofs to enforce correct behavior. And for the public key variant, the zero knowledge proofs are actually quite easy to find, like off the shelf. But for the secret key variant, we actually needed to develop our own zero knowledge proof. So that can be seen as a contribution of independent interest. Okay, and I just want to briefly show you what is the communication pattern that like our protocol has. So for certain parameters that are not explained here, and the secret key variant, each party will begin computing their own message to send. This is the time that it takes in a very decent laptop. It's not even like a very beefy server. And then each party is going to send the message to the other party. This is extrapolated in a 600 Mbps network. Then more local computation from the messages they received. And we see that from beginning to end, the timing is actually pretty competitive. We're talking about almost 2 seconds for the whole computation because this message is simultaneous. And I know it's hard to get a comparison, like how is this efficient in practice or how does it compare to other works? Well, I have this table that I just want you to look at the bottom part of it, where we compare this, like these are the numbers for the basic like homomorphic encryption-based protocol in which one party sends to the other one computes and returns based on that computation. And in this case, we see that just the time that it takes to Alice to process the first message locally is like 14,000 milliseconds approximately. And then she has to send this, and then Bob has to process. It takes 1 second to Bob, and then it has to return back. Not even counting communication, we're already way above like the 2 seconds. We're talking about 2.5 seconds. So we have a more detailed comparison in our paper, but it gives an idea that this is indeed an improvement with respect to other protocols. And with that, I'm ready to conclude. I invite you to see the full talk, the full paper, and I'm open for questions. Thank you.
Thank you. I also don't have any questions in the question and answer panel, but we also don't have too much time left.
I understand.
Unless there is any burning question from the panel.
I have a quick question.
Yes.
Yep.
Thanks, Daniel.
Happy to. Yeah.
The question is whether OLE is also interesting for bits or only for larger field elements.
So you mean like what happens if the ring is like just F2, for example?
Yes.
Okay, well, if there in OLE, if the ring is F2, you can show that this collapses down to oblivious transfer. So whether or not this is interesting is, of course, whether or not oblivious transfer is interesting, which is the answer is, of course, yeah. So it still has the same applications as oblivious linear evaluation, MPCE, and so on. But oblivious transfer on its own can enable many other things. So you can typically find constructions that are more optimized for that particular setting. Like I don't think you typically take an OLE construction instantiated with Q equal to 2, and then suddenly have an OT protocol. Like you typically go like you use different constructions to get like OLE over F2.
Sure. Thanks.
Any more questions? Let's proceed to the, thank you very much again.
Absolutely, thank you.
And we proceed again we go to the third paper, which is to be presented by Kamit again.
Yes, let me
Share your slides, please.
slides.
Now she will talk about multi-client verifiable computation via conditional disclosure of secrets.
Right, this is working.
Yes, it works.
Hi, so this work, multi-client verifiable computation via conditional disclosure of secrets. This is a joint work with Rishabh Bahaduria. Okay, so CDS is a generalization of secret sharing where two parties, let's call them Alice and Bob, they share a random string R, and they wish to disclose a secret S to a third party, condition on condition on the fact that some predicate, the output of some predicate equals 1, or satisfies some condition on the inputs x1 and x2. And CDS is defined by two encoding algorithms, one for Alice and one for Bob, that respectively compute the messages M1 and M2, and a decoding algorithm for Claire that extract the secrets. And note that the original definition of CDS does not maintain privacy. So CDS was introduced in the context of private information retrieval, and had also found applications in the secret sharing and the attribute-based encryption domain. And in the past decades, there were quite many works trying to understand different aspects of CDS, like communication complexity, randomness complexity, the complexity of the decoder, and the expressibility of CDS. What kind of class of functions can be captured using CDS and under what assumptions? And regarding this aspect, let me just say that the Garbage circuits, we can use Garbage circuits to construct CDS for any efficient function. under the assumption of one-way function, but the complexity of the communication complexity between the of the messages M1 and M2 will grow with K times C, where K is the security parameter and C is the size of the circuit we want to compute. And the goal of this work is to achieve better rates. So, in this work, we explore the observation that for CDS with sufficiently long secrets, the secret can serve as a proof for the fact that the output of F equals 1. So, meaning that every CDS construction supplies integrity mechanism for this predicate F. And let me just say that also this observation is not new. It has been used by Parnod al. In the context of attributes-based encryption, which is a public key analog for CDS. And here we exploit this mechanism to demonstrate this usefulness of CDS for designing a non-interactive two-client verifiable computation in the presence of an untrusted server for a class of predicates that we construct CDS for. So, in this setting, we have two clients, and they wish to delegate their computation to an untrusted server, but they also, meaning that they want to check the correctness of the output from the server, and they want to do it with less overall work than recomputing the entire function again. And in this scenario, what typically is assumed that the server is maliciously corrupted, and any subset of clients is semi-honest corrupted, and the clients cannot collude with the server because then, correctness is gone. Okay, so let me just recap. When I'm saying semi-honest adversary, then I mean a benign adversary that follows the protocol specification, while an active or malicious adversary can attack arbitrarily the protocol. So how is it working? How is this construction working? Given two CDS for F and F bar, the parties, we use these CDS to construct verifiable computation. And again, this is based on already prior work. So basically what you do is that you have two secrets and you encode them for both for the two CDS. And based on the output returned from the server, it is possible to learn whether the outcome is of F is 0 or 1. And from the security of the CDS, the server should not learn more than one secret from these messages. Okay, so now the basic model that we consider in this paper, we have three parties. We have Alice, Bob, and the server, and they're shared. They have, there's a setup phase where they share a random string, and a third untrusted server, which is going to emulate the role of player. And our constructions can also be extended for more than two clients. Okay, so. We prove malicious security in the presence of a single corruption and the server, and we apply our constructions to specific set of predicate as opposed to previous work that used global circuits that can be applied to any class of function. So I'm pretty sure I don't know how much time I have. Pretty sure I don't have much time, but let me just quickly summarize our results.
Have some time.
Sorry.
Still have some time.
Oh, okay, great. So, so in this work, we explore the connection between multi-client verifiable computation and CDS for a particular class of predicates while achieving better rates, better communication complexity. Our constructions are secure in the presence of malicious server and also malicious clients, not just malicious servers, but the servers and the server and the clients cannot collude. We also introduce, in order to get simulation-based security, we extend the basic definition of CDS into two additional notion of private CDS and oblivious CDS. I'll say in a minute what do I mean by that. And based on several tools, we construct new classes of private CDS for equality, inequality, private set intersection, cardinality, and more. Okay, so let me just say quickly the advantages of using this. Why do we want to use CDS as a tool to get to protect against malicious security? It has several advantages. First of all, that the constructions are non-interactive, requires only sending a single message from Alice and Bob to Claire. You can actually do batch verification, because verification is very simple. You just want to check whether the secret is correct or not. So you can amortize many verifications, and that also reduces the rate of the message sent from Claire to Alice and Bob. And the setup is very simple, as opposed to other protocols that require more complicated setup, like random OT, random multiplications. Here, the setup is just a random string. That's it. So it's much, much simpler. And quickly, the two variants of the CDS we consider in this work are private CDS and oblivious CDS. Remember, in the original CDS definition, privacy is not implied by the definition. In private CDS, we require that Claire does not learn anything about X1 and X2, meaning that these are not known to Claire, not part of the decoding procedure. And oblivious CDS means that Claire cannot distinguish between the case whether it learns the secrets or not. And just as a taste, here is an example of oblivious CDS for equality. The parties can use their inputs X1 and X2 to create a 1-degree polynomial, where Alice can embed the secret in the polynomial. And the way they constructed polynomials, you can see that the secret can be extracted only if they have X1 equals X2. And we want to, let's just say that here Alice and Bob are semi-honest, passively secure, and if you want to extend it to the malicious setting, so we use an additional tool of Sigma protocol, and we rely on the verifiability of Sigma protocol to achieve security against malicious either Alice or Bob. And the idea is that the fact that if we have multiple transcripts, we can extract something, we use it to extract the secret. So we use slightly different ideas for achieving equality and inequality, but around the same ballpark of constructions. So this was just a taste of the constructions we achieve, and that's it. Thank you very much.
Thank you. We have 1 minute for questions, if there are any. There is nothing in the Q&A panel. If not, then let's thank Kamit again and move on to the next presentation, which is will be given by Daniel Slamani, I think.
Yes, hi.
And it will be about fully collision resistant chameleon hashes from simpler and post-quantum assumptions. Can you please share your
sure.
screen?
So do you see screen?
Yes.
So, okay. Hi, everyone. So I'm going to talk about the constructions of fully collision resistant chameleon hashes from simple and post-quantum assumptions. And this is joint work with David, Stefan, and Kai. Okay, so what is a chameleon hash? So basically, a chameleon hash is a hash function which is parameterized by a public key. And to do some hashing, you take the public key and take a message and some randomness to compute the hash value. And given the message and the randomness, you can check the hash. And there is some additional information associated to the public key, which is the trapdoor, which is a secret key. And if you have the secret key, then the secret key allows you to explain this hash value for different messages. So basically it means that you can compute randomness that explains this hash for a different message. So basically you can think of a trapdoor commitment, right? So that you compute and then you can open in different ways. So what you want to have from that is that as long as you don't know the secret key, you have collision resistance. And another property that is important for applications is that you have indistinguishability, which basically means that if you see the randomness and the hash value in the message, then you have no idea whether this comes from the original hashing or whether you have computed a collision for it. Okay, so what's the motivation for having chameleon hashes? So they are quite frequently used in different primitives. So in basic cryptographic primitives like constructing tightly secure signatures or online-offline signatures, sanitizable signatures, and so on, a very prominent application is to lift non-adaptively secure signatures to adaptively secure ones. And they're also used in encryption schemes, and increasingly we see that they are also used in like larger constructions like editable or redactable blockchains in very different flavors. Okay, so what's the motivation for this work? So there is a recent work from PKC20 that somehow classifies the security properties of chameleon hashes. And what they did in this paper is the introduction of a strong notion of collision resistance, which is called full collision resistance, which is basically the most natural notion of a collision resistance notion that you could come up with. And it's definitely the strongest one. And if you come back to trapdoor commitments, then this would be one that satisfies the weakest collision resistance notion, which basically means that the chameleon hash is collision resistant, but if you see a single collision, then everything is, all your security guarantees are gone. So if you think of like Peterson commitments, if you see two different openings, then you can extract the secret key and everything is lost, right? And these stronger notions try to give the adversary more power in order to guarantee collision resistance, even if arbitrary collisions are seen. So I will not talk about the indistinguishability notion in this short presentation. So, okay, so let's look at the state-of-the-art, the constructions. So in the PKC paper, there is a generic template to construct fully collision-resistant chameleon hashes. But what is required is that you have to use a perfectly correct public key encryption scheme, which basically means that this doesn't allow you to instantiate it from post-quantum assumptions in an efficient way, right? You could use compilers that like amplify and get rid of the correctness error, but it won't lead to practical instantiations. And the only practical instantiations of chameleon hashes in such a setting are known for the weakest notion of collision resistance, which basically is that of a trapdoor commitment. And what we do in this paper actually is we show that we can modify this compiler in a way that we can construct fully collision resistant chameleon hashes without relying on public key encryption. And we also achieve some other properties that I'm not going to talk about here in this short presentation. And we can then instantiate it from post-quantum assumptions. So just to recap what this full collision resistance notion means. So basically what you do is the adversary gets your public key, but has then adaptive access to a collision finding oracle. So it means you can put arbitrary stuff in there. The only condition is that the hashes that he puts there are valid, but then he can see arbitrary collisions for messages of its choice. And the adversary wins if he can come up with any non-trivial collision. And this basically guarantees that you have malleability, non-malleability on the hash and the randomness as well, and which is arguably the most natural notion that you want to have. So how does the template of this construction looks like? So the idea is basically that you take a non-interactive commitment scheme, and then you commit to the message, and then you add a simulation extractable non-interactive serial knowledge proof that either you know the opening of the commitment and the commitment public key, or you know a pre-image under a one-way function where the image of the one-way function is part of the public key. And then to check the hash, you just check the validity of the proof for the given hash. Okay. And what this means is that it allows us to get rid of this, like relying on perfectly correct public key encryption, and we can use standard non-interactive commitments. And as we show in the paper and also in the full presentation that Kai has done, is that this allows us to instantiate this generic compiler under different assumptions. So we show one concrete constructions on the discrete lock assumption, and we also show a concrete construction under the LPN assumption, and we can equivalently also instantiate it from the LWE assumption. And basically, and in addition to that, it offers better privacy guarantees as it provides a stronger indistinguishability notion than what previous work has done. Okay, so that's all from me. So thank you very much for listening, and I'm happy to take any questions. So if you want to have any further insights, then please look at the paper. It's an e-print, or also at the presentation that the full presentation that Kai gave.
Thank you. There is no questions in the Q&A section.
So,
can you explain, you said in the beginning that there is application to blockchain.
Yes.
Can you explain what the applications are?
Yeah, so the idea is basically that you have, so there are different approaches, but the most, I think, natural idea is that if you put transactions or like hash trees of transactions into the blockchain, then you could use a chameleon hash instead of a normal hash function, which would allow you to rewrite transactions that you already have recorded in the blockchain. So you could later decide to change something that is already recorded there, which clearly would not be possible if you would use a normal hash function.
Is it actually used, or this is too new to be implemented in? Have you implemented it?
So I'm not aware of any concrete implementation in some products that's used. I think there was some project with Accenture that were doing that, but I have no idea if that's really used. But it's, at least in the research community, there are quite lots of works popping up that are relying on these kinds of concepts.
Okay, thank you.
Thanks.
Any other questions? If not, thank you again.
Thank you.
And we move to the last presentation for the session, which will be given by Raluca. Can you start sharing, please?
Can you hear me?
Can you start sharing your screen?
Yes.
She will talk about generalized Matsui algorithm 1 with application for the full DES.
Thank you.
Floor's yours.
So my presentation is based on a work that is joint work with my colleagues Tomer Ashur, Danilo Siacic, and Steph Dazelier. The contributions of our paper are threefold. First, we introduce a new type of attack based on linear cryptanalysis called the strictly zero correlation attack. We used these new techniques in order to design a new attack covering the full DES. And this new attack aims at recovering the key bits based on a key-dependent behavior of the linear trail. Initially, we designed a one-round poisonous trail for DES. This meaning that we designed a one-round linear hull for DES. If we fix the input and the output masks as alpha and beta, the values on the slide, we can notice that we have 4 different values for some intermediate masks. Therefore, we have 4 different trails. Each trail can have a different correlation and involves different key bits. Therefore, the correlation of the entire hull can take 3 different values, depending on some key bits constraints. We call this a poisonous trail based on the way we compute the correlation of a linear trail. If we have a trail based on many rounds of a cipher, we usually multiply the correlations of each round. Therefore, if the correlation of one round is 0, then this value will act as a poison, and poisoning basically the correlation of the entire hull. the entire trail. After that, we extended our 1-round poisonous trail to a 2-round poisonous trail. And note that the input mask here is one of the values used in Matsui's trail. So we managed to extend or to adapt Matsui's trail by replacing the last 2 rounds with our 2 poisonous rounds. Note that the values of the correlation, since the values of the correlation can take 3 different values, this means that the keys are divided into 3 different key classes. Therefore, just by observing the value of the correlation, somebody can learn something regarding the, some constraints regarding the key. Therefore, we used this property in order to design a key recovery attack that is pretty straightforward. The attacker has to initially compute the correlation of the trail by using 2 to the 51 plaintext ciphertext pairs. We computed this data complexity according to the smallest non-zero value of the correlation. After that, the attacker has to compare the empirical correlation to the 3 expected values and basically learns the key class in which the master key belongs. We performed experimental verifications in order to prove our hypothesis. We also used 2 to the 51 data. We used a hardware implementation based on a custom DES accelerator. We performed 48 experiments for each key class, leading to a total of 144 experiments. And in order to interpret our results, for each key class, we computed the base 2 logarithm of the absolute value of the mean of the empirical correlations. So in the table, you can see here the expected weight, the theoretical weight, the weight that we computed using the formula I presented before, the key constraints met by each key class. You can notice that our experimental results are pretty close to the expected ones. But since they are not exactly similar in our work, we also questioned the presence of the linear hull for the entire DES. And we proved that it indeed exists. And also you can see the success probability that key is recognized in the correct class. We went a step further in the interpretation of our results, and we plotted the distribution of the empirical correlations from the experiments, which are marked with green. And we compared them against the histograms of the respective expected values, which are marked with blue. All our experiments support the hypothesis that different key classes indeed can be distinguished. Therefore, the correlation discloses the constraints that the key fulfills. In conclusion, in our work, we constructed a zero correlation key-dependent linear trail for more than 1 round of DES up until full DES. We used this linear trail to design a key recovery attack on the full DES, and we performed experimental verifications of our claims using a custom DES accelerator. Thank you for your attention, and if you have any questions, please ask now, or you can use our emails to further communication.
Yes, thank you. It seems everybody is very shy. There is no questions again. I was wondering, can you use this technique for any other cipher than this? Have you, or it's only this specific?
We think this is possible. Of course, the cipher has to exhibit the property that you can have in 1 round the Hall effect, and of course the key-dependent Hall effect. For example, I don't think AES can be attacked using this technique, but I think that there are other ciphers that can be vulnerable.
But you haven't tried with other ciphers?
So far, no.
Mm-hmm. Okay. Any other questions? If not, let's thank all the speakers of the session. This was the last talk in this session. Thank you very much. Fortunately, silent thank you to all of you. And we'll have a coffee break, I guess.
Yes, we are a little bit behind. So I suggest, again, to keep the schedule, and we'll start at a 4:15, I think.
Yes.
That's the official time. So we'll be back again in something like 20 minutes, more or less. Okay?
Thank you. Bye-bye.
Thank you. Bye.
Thank you. Bye.
Before I forget, you have received an email for the closing today. So we are organizing this get-together party. So get something to drink and we'll talk a little bit, you know, out of the recording. So I'll see you later.
Okay, so hi everyone. I'll be chairing this session about MPC and ORAM. And the first talk will be on black box constructions of bounded concurrent secure computation by Xiao Liang.
So I can start? Okay.
Yeah.
Let me share the screen first. Okay. Thank you for the introduction. My name is Xiao Liang. I'm going to talk about black box construction of MPC protocol achieving the notion of bounded concurrent security. This is a joint work with Garg, Pandy, and Visconti. Oops. So MPC is a very important tool, but in today's complex internet environment, we found that this is not usually enough. Highly concurrent security is usually required. So to address this issue, Conetti proposed the notion of universal composability. It basically achieves the strongest security notion as one can hope for. However, it comes with a price. There are no lower bound if you don't want to use any setup assumptions. So people start seeking alternative notions for concurrent security without setup. For example, one notion is bounded concurrent security, which means the fixed set of party executing the same protocol, but with a prefix number of instances. In different instances of the same protocol, the same party may play a different role. So this is sometimes called the security with interchangeable roles. And there's also other notions such as SPS security, which means that we give up a little bit on the security set. The simulator now can run in super party nominal time. And also there are other notions which I won't mention here, but this work is only on bounded concurrent security. We will also mention a little bit about SPS security because there is a GKP protocol which is closely related to our technique. Okay. So our contribution can be summarized as follows. We build the first bounded concurrent MPC protocol, which is black box, constant round, and assumes only OT and hash function. Our result can be interpreted as a black box version of pass04, but pass04 assumes trapdoor permutation plus hash function. So we also improve a little bit on the assumptions. Okay, as mentioned before, our starting point is the GKP protocol, which is already bounded, black box, constant round, and from OT and hash function. However, it achieves SPS security. The reason is in their protocol, there is a commitment. The simulator needs to run super polynomial time to break the commitment to finish the simulation. So we observe that it is sufficient if we can replace that commitment by a straight line extractable commitment. Then we will have the protocol as satisfying our need. I won't go into the details for the reason, but since we only have 5 minutes, so trust me, like, if we can build such an extractable commitment, then we can have our result. Of course, when we are doing this, we have to make sure that our new commitment is a black box, constant round, and do not incur any new assumptions. So our starting point is the Barak Lindo extractable commitment. I list the whole protocol here, but you don't need to like read everything. You just need to focus on 2 points. First, this commitment use trapdoor commutation. This is something we want to remove. Second, if you look at the 3rd round and the 4th round, it's essentially a black box commitment proof from the receiver side. It makes non-black box use of the underlying commitment. We want to fix this also. So how to do that? There is a way to replace trapdoor commutation by OT. So you don't need to read it. I just want to let you know that we can do that. I want to focus on the 2nd point. This is a commit and proof protocol. We found that if we are using the protocol from a work of Goyal, Ostrovsky, Scafaro, and Visconti, then we can make this black box because they build basically they build a black box commitment proof from hash function. It seems weird then. However, this protocol in its current setting only achieves security in the standalone setting. But remember that this protocol will be used as a building block in a large protocol, and we want security in bounded concurrent setting. So this is not enough. We need to make this step to be this step is zero knowledge, but we need to make it bounded concurrent zero knowledge, right? So the key observation is that we are in a bounded setting, bounded concurrent setting. So we have the control of the other of the communication of the other parts of the protocol. So it's sufficient if we can build a L robust zero knowledge, which means zero knowledge when as long which means the protocol which is zero knowledge as long as the external communication is bounded by some prefixed parameter L. So we show like how to build it by combining the Barak's famous non-black box zero knowledge protocol together with a GeoSV trick to make it black box. Yeah. With these techniques, we show that how to replace this, how to modify the GeoSV zero knowledge protocol to be black box version, and achieving this L robust ZK notion. Yeah. Then for more details, we refer the reader to our full version of the paper. Thank you.
Thank you, Xiao.
Yeah.
I don't see any Q&A. Anyone is? Yeah. There was a. All right. So I had some question. Which setting did you target? Like active or passive, and honest majority or dishonest majority?
We are targeting at the active malicious security setting, and it's a static. Like you can prefix the number of parties you want to corrupt. We don't achieve the active. We don't achieve the active corruptive notion. And what's the other question you have?
Honest majority.
No. You can corrupt more than the majority of the honest parties. Yeah.
So there was a work by Damgard and Ishai from 2005. You referred to their work?
I don't think so. Yeah, I'm not familiar with that work. Maybe I can check offline. Sorry.
Yeah, let's talk offline. All right. Any other questions? All right. So thank you, Xiao.
Thank you.
And the next speaker is Xiao Yang, right?
Yes.
Hi, so you want to share your screen?
Okay.
All right, so the next talk would be communication efficient, proactive, secure computation for dynamic general adversary structures and dynamic groups by Xiaoyang Huang.
Can you see my screen?
Yes.
Okay, let me start. Hello, I'm Sayan Huang from UC Irvine, and I'm going to talk about the communication efficient, proactive, secure computation for dynamic general adversary structures and dynamic groups.
Sorry, we don't see your presentation, only your desktop.
Oh, sorry. Let me stop and reshare it. Oh, excuse me. How about now? Can you see the screen?
Yes, now it's perfect.
Okay, thank you. Okay, this is a joint work with Karim El-Dafari, Raphael Starubsky, and Moti Young. Proactive MPC is an MPC scheme that is secure against mobile adversaries who can eventually compromise all the parties as time goes by and obtain the secret value. Previously, our works on proactive MPC were based on the threshold adversary model that limits the adversary's corruption capability by a threshold, which means the number of parties that can be compromised at the same time. However, the adversary's corruption capability can be specified more generally by a so-called general adversary structure. General adversary structure defines an adversary's corruption capability with a set of corruption scenarios. That means a trusted third party defines GAS, which consists of these three structures. The access structure defines which set of parties can obtain the secret value with their shares. And the secrecy structure defines which set of parties cannot get any information about the secret, even though they combine all their holding shares. The adversary structure, which is a subset of the secrecy structure, defines which set of parties can become corrupted by an adversary at the same time. So what we did is to construct a structure-adaptive proactive MPC on dynamic GASs, which means the protocol can adapt to the dynamically changing groups and GASs. Normally, MPC consists of the following four protocols: share, reconstruct, add, and multiply. On top of them, so two more protocols called refresh and recover are required to make it proactively secure. Refresh is to proactively re-randomize the shares, and recover is for randomly rebooted parties to recover their shares with the other's help. So in our work, we made these two existing MPC schemes on GAS to be proactive MPC by building up these two protocols. And note that both are secret sharing based MPC, and while one is based on the monotone spend program and the other is based on the additive secret sharing. As a second contribution, we consider the dynamic groups. And in dynamic groups, participating parties can leave or newly join in any time. However, the leaving parties should not be able to use their shares to get any information about the secret. And also, the newly joined parties should get some shares that can reconstruct the same secret. And naturally, as group changes, the GAS should be also changed. This can be done by the protocol called redistribute that redistribute a new sharing of the same secret to the new group. So by adding this protocol, the PMPC now works on the dynamic groups as well. And note that there were only a few previous works considering the dynamic groups. And now, since we are considering two kinds of MPC schemes that are based on two incomparable values, when the GS is changed, the parties need to decide if they're going to use the same scheme or to change the scheme to the other. So if they decide to use the same scheme on the different GES, then they can use the redistribute protocol to adapt to the new GES. But if they want to convert it to the other, then the conversion protocols from MSP-based shares to the additive shares and the opposite directions are required. So we just suggest the share conversion protocol between the MSP-based PMPC and the additive PMPC as our third contribution. So to summarize, we make two different secret sharing based MPC schemes on GAS to proactive MPC by adding two protocols, refresh and recover, and make it work also on dynamic groups by adding the redistribute protocol. And also we suggest the share conversion protocols between the MSP-based PMPC and the MSP-based shares and the additive shares so that more efficient scheme can be used depending on the dynamic general adversary structure. So due to the time limit, lots of details are omitted in these slides, and I only introduce the overview of our work. So please refer to our full version of the video and the paper if you're interested. Thanks for your attention, and I'd be happy to get any questions.
Thank you, Xiao Yang. So there is a question by Daniel Esteban. So is it restricted to some type of adversarial structure only, like Q2 or Q3?
Yes, so it is limited, restricted to the Q2 adversaries.
All right, thank you. I have a quick question. Did you think of some concrete example of in which scenario this model would be like necessary?
Yeah, so as a one application for this setting, it can be a DevOps system, which is a commonly used managing methodology for the large network systems like public clouds or private clouds or the big companies. And there is a specialist who manage this DevOps systems, and especially it's called SRE in Google. So in that system, SRE can define this GAS and distribute it to the servers through a secure CNC server. So yeah, that can be one application for this.
All right. So thank you, Xiao Yang, and we'll proceed to the next.
Thank you.
Right. Hi, Ben. Want to share your screen?
Can you see my slides?
Yes. So the next talk would be on private identity agreement for private setting functionalities. And the speaker would be Ben Turner.
Okay, great, thanks. Yeah, so I'm going to talk about some applications that we have, just protocols to extend what we can do right now with private set functionalities. Okay, so private set functionality, the main idea here, the goal of what we're pursuing, say we have a two-party computation in which Alice and Bob both have a database, and they want to make queries to the join of the two databases, right? So in your ideal setting, both parties are going to give their database to some third party. Third party is going to compute the join of the databases and allow Alice and Bob to make repeated queries to the join of the databases and get the right answers. And this actually turns out to be very useful in practice. There are a couple of large tech companies that currently use PSI with aggregate statistics. And you can think about how they work. It's really just two steps. First, you have to assume that both parties have primary keys or unique primary keys for the rows in their databases, such that if both parties have rows that correspond to the same user, then they have the same primary key. Okay, so first you do a PSI on the primary keys, and then once you compute the primary keys, this basically acts as your join, and you can aggregate all of the data that's been associated with those primary keys. Okay, so this is used in practice all the time. The central question of this work is to say, what if we don't already have those primary keys? So how do you agree on reusable primary keys that we call identity agreement? And this is also, it's very similar to some work that was put on ePrint earlier this year by a group at Facebook, but slightly different. We have a twist that I'll talk about why our version is less efficient and a little bit harder to do. Okay, so to do identity agreement, we're just going to make an assumption first on the parties' databases that each party has some identifying information about all of the users in the database, right? So you can collect names, you can collect phone numbers, you can collect email addresses, you can collect physical addresses, and we are going to say, we're going to assume that both parties have information about their users, but they may not all have the same information. Okay, so Alice might have a name, phone number, and email address for one party, and Bob might not have the email address, but might have a physical address for the other party. And we still want to be able to compute the join. And in general, the rule that we're going to use is that if any of the elements of identifying information match for a single, for two rows, then we're going to say that they're going to belong to the same user. And the key is that really what we have to do is we have to come up with some abstract notion of an identity. So we're going to do that, and we're going to really cast this problem into a graph problem in which we're going to say, look, each party has a database. Well, I'm going to look at the database as a graph. So to make the graph, I'm going to say every piece of identifying information in Alice's database is going to be a vertex in the graph, and I'm going to make sure that there's a path between every two vertices in Alice's graph that represent the same identity or the same user. So you can look at this graph as a big graph of small connected components, which every connected component represents what Alice thinks is one user. And we're not going to make the assumption that Alice already knows that every row in her database belongs to one user, right? So Alice could have 2 rows or 3 rows that she doesn't know actually belong to the same person in real life. And we're gonna deal with that a little bit later. We're gonna deal with it down the line. Okay, so now Alice has a component for every identity, right? And we're going to say Bob does the same thing. And now we can imagine that there's going to be some big graph G in the sky that represents the universe of all of distinct identities and all of their information. And we do have to assume that there are non-overlapping sets of information. Okay, so now what we're going to do is we're going to say, look, we can, once we've represented the our databases in this way, we're going to construct a protocol that allows us to assign primary keys or unique identifiers to all of the identities in the 2 parties' graphs. And the way that we do it is we say, look, as a first step, Alice and Bob can invoke a protocol that reconstructs the big graph G in the sky to the best of their ability. And then once they've done that, they can assign unique labels to every component in the combined graph. And then as output, for every row in each party's database, they can get the component label from the combined graph. And you can see here in this little example that Alice had 2 different components that she thought in the beginning were different users, but in fact Bob has some information that so-called connects the two components. So Bob has information that means Alice might be able to condense one of her rows. Okay, and this is an important observation, and the observation tells us that whenever you have an ID agreement protocol to really set up these primary keys that you're later going to use for set intersection, first you have to output encryptions or shares of the primary keys. And we do want to output these intermediate values so that you can reuse them again and again for subsequent PSI protocols, right? And then the subsequent PSI protocols, whenever you're going to compute different aggregate statistics over your join, they're going to take encryptions or shares of the primary keys that you computed. And once again, just want to really hammer home on the privacy issue, right? We have to output shares or encryptions of these keys, because in the ideal setting, the ideal functionality would never leak to Alice or Bob whether one party could connect 2 rows in the other party's database. Okay, all right, and this is specifically the example that if Alice ever gets a situation like this, it means that Bob must have some component in his graph that allows you to condense 2 components in Alice's graph together. Okay, so those are the main ideas. We implemented this for the honest but curious setting using oblivc. You can see this is just a diagram of all of the components in the garbled circuit. You can refer to the full talk or the paper for all the information, but the performance was fairly good. Like we could do about 2 million users on each side and on the order of a day. Okay. Depending on, do I have a lot more time? So I can just, yeah, just like show some, show you some graphs. This is the how long it took to run for 3 security parameters. Security parameters are on the collision probability. So you have to, as a first step, you hash all of the identifying information, and you don't want collisions in the hashes. And then you can see that this is just the same graph again on a linear scale on the input size to see how long it takes. And that's all I got.
All right, thank you very much, Ben. What is the y-axis here?
Oh, minutes. Minutes to run the garbled circuit. We did it over LAN on GCP.
Mm-hmm. All right. Any questions?
Yeah, quick question. So when you mentioned that Alice in some examples could merge her rows together, does that mean the data she had for each of the 2 rows beforehand were in disjoint columns?
So, okay, so when Alice has two rows, like Alice has 2 rows that represent the same identity. So right. She might have slightly different names or different addresses, right? She might have for example, a row that she doesn't know a name for it. She has an email address and a physical address, right? And she has another row with a name and maybe a different physical address and a different email that the person supplied, something like that. Mm-hmm. And the hard part is that we have to do this cleaning step in order to merge those rows.
So if they're not disjoint columns, then how do you merge conflicts? Like, 2 different email addresses in the 2 different rows?
So the point is that Alice thinks that these are distinct users. Uh-huh. So and Bob is going to come along, and maybe Bob is going to say, actually, I have information from your 2 different rows in the same row in my database.
Yeah, I'm just wondering, logistically now Alice has 2 different emails for the same user.
Yeah, well, that could happen.
Okay, so you just union then.
Yeah, so the full component is going to have the union of those 2 email addresses. Mm-hmm. Yeah, the big graph, the full connected component is going to have both of those email addresses.
Okay.
All right. I have another quick question. Could you reduce this problem to performing PSI on each of the primary keys?
The question is, how do you get primary keys? So in some sense, you are doing a PSI on all of the different columns in the database, but then you also have to connect them. And so you could do a PSI on the step that that finds the primary keys, but the hard part is connecting.
Because you want to output each record only once?
Yeah, you want to output a unique, like one what's it called? One primary key for all of those different pieces of information.
I see. Okay.
Yeah, it's a good insight. And basically, that's what the construction does. It does PSI for all of the columns, and then there's a step that combines.
Mm-hmm. All right. So, thank you very much. Mm-hmm. All right. So, Willie is the next speaker.
Can you hear me properly?
Yes. All right.
Can you see slides?
Yes.
Wait, I'm not sure. Can you see the display mode here?
Yes, yes, we can see.
Yeah.
So the next talk is UC Secure OT from LWE, revisited by Willy Quash.
Yeah, thanks Avishai for the introduction. So as the title suggests, this work is about oblivious transfer from the learning results assumption. So let us first recall what's oblivious transfer. Oblivious transfer is a protocol that's executed between two parties, sender and the receiver. So the sender has two messages, M0, M1. The receiver has some choice bit B, and they will. The goal of the protocol is to have the receiver receive the message MB in the end. So what we're considering in this work is true message OT, where the receiver first sends a message to the sender, and the sender responds with one message to the receiver. So what we would like at the end is the receiver to derive the message MB, but we would also want some notion of security. And in particular, what we would like is that if a honest sender is interacting with a corrupted receiver, then in some sense, the corrupted receiver shouldn't learn any information about the other message, M1 minus B. And if the receiver is honest receiver is interacting with a corrupted sender, then the corrupted sender should not learn any information about the choice bit of the receiver. Okay. So to be more precise, what kind of security we consider in this work? So how do we model the adversaries that we are dealing with? We are dealing with malicious adversaries. So here, all the corrupted parties could behave maliciously, kind of not according to the specifications of the protocol. And to be more precise, what we're considering is a simulation-based security notion. So our definition of security will allow to have some composability notion that will be formalized in the UC framework. That's the only place in here that I'll talk about UC. And the main drawback is that it requires a trusted setup. So the cost of having this composability property, so that the oblivious transfer can be securely executed like within a much larger protocol, is to require a trusted party to generate a CRS honestly. And then another orthogonal direction where we can give power to the adversaries, whether we consider adversaries that are computationally bounded. So here, ideally, we would want to ensure security where the adversaries are computationally unbounded. And it turns out that we cannot have statistical security, so such a security for both parties, but we can hope to have such a security for at least one at a time. Yeah, so how do previous constructions of OT work? What do they achieve more precisely? It turns out that we actually don't have that many constructions of similar, like UC secure OT from standard assumptions, but there's a very nice one, in particular this one by Pikert, Vaikutanathan, and others, that achieve essentially everything that we want. So it's simulation-based, so it will be composable. And depending, it has two modes of operations, and according to the mode of operation, it will either guarantee statistical sender security or statistical receiver security. So that's really good. And also it can be instantiated from many different assumptions. So in particular, as far as I know, if you need a kind of simulation-based secure OT from LWE, that's essentially what you lose. Okay, so what's the problem if the PVW OT is so nice? Well, actually, if you look at it, and especially if you look at the LWE side of it, there will be a very slight nudge. And what's this slight nudge? Well, actually, what I said in the previous slide is actually a bit off. In particular, the construction of OT from LWE in the PVW paper only achieves a weaker kind of security than what I described. So more precisely, the receiver security that they get is always computational. So as far as I know, like before this work, we didn't know how to get statistical receiver security in the simulation-based security, and the CRS can be only used once to argue security. So if you have a sender and a receiver and they want to send several messages, the CRS can only ensure security for one execution. After that, you will have to throw away the CRS and require a trusted party to generate a fresh CRS. And again, I didn't lie everywhere, so you actually don't have such problems for either the DTH-based instantiation nor the QR one. So that's very LW-specific problem, and that's kind of strange. And our contribution in this work is to kind of smoothen the nudge. And we show that there's this, how to build such a simulation secure OT that can be either statistical secure for the sender or the receiver, depending on some mode. And we prove that, we prove security under the LW assumption. So presumably post-quantum, if you care about that. So to be more precise, that gives in particular an OT that can be statistical receiver secure if you wish that to be so. And as far as I know, that's the first construction of that. And on top of that, the CRS is reusable. So it also eliminates the second issue I was talking about. And the cost of that is to rely on we rely on a slightly stronger assumption. In particular, the LW modulus that we have to use is now sub-exponential instead of polynomial. And just to give a very quick two-liner about what we use to build such an OT, the main primitive that we have to build as an intermediary step is a special kind of encryption scheme from LWE, where public keys are sparse. So there are very few valid public keys. But if you consider this the larger set in which those public keys live, and you sample a public key independently, uniformly in that, and try to encrypt the message using such a public key, then those public keys will information theoretically hide the message. So in some sense, most of the public keys are kind of garbage, and we will actually not encrypt properly in this very strong sense. And moreover, what we want is to have a trapdoor way to identify such public keys in a time that is essentially independent of the modulus Q that we want to use for the LW assumption. So that's the main intermediary primitive that we need to build. Yeah, that's all I have to say. Thank you for your attention. And yeah, if you have any questions, happy to take them.
Thank you very much, Willie. I don't see any questions in the Q&A. Does anybody from the panelists wants to ask? All right, so no questions. Thank you again. All right, the next speaker is Samuel.
Hello.
Hi. So, you ready?
Can you see my screen?
Yes. Right, so the next talk would be oblivious tight compaction in order n time with smaller constant by Samuel Dittmer.
Great. This is joint work here with Rafi Ostrovsky. I'm just going to try to give some of the motivation for the algorithm and a very high-level description of the algorithm itself without digging in too much to actual computation of constants. So first, tight compaction. I'm going to give just a quick visual representation. You have blue and red elements. You want to push the blue elements to the front. Notice that the relative ordering of the blue elements has changed. So this is not a stable tight compaction algorithm. And as we will see, this is sort of inherent. And I'm going to throw up the whole, here's the formal definition of what oblivious tight compaction is, but just a couple of things I want to note here. This works by the client interacting with a server and giving a series of commands to the server to access certain memory locations. those commands need to be data independent, either predetermined or just totally random. And then notice that the client has essentially no local memory. And so all they can store is the most recent element they grabbed. And as sort of an exercise to the reader or a form of motivation, I want to ask this modified version of the question. So if you remove the restriction that the client has finite memory, but they're still only allowed to just tell the server to swap to adjacent, well, not to adjacent, but to swap the identified pairs or not to touch them, how small can your list be? So you have a graph and you visit the edges in some predetermined order, and for each edge you order swap or don't swap. How few edges do you need? I think the answer is probably very small, like on the order of like 2n, but it's a nice exercise to think about. So what can tight compaction be used for? At a very high level, I think we can just say that it can either be used as a weaker replacement for ORAM to just do a simple task like delete half your server, or as a building block inside of ORAM. And it has some other applications in like networking and routing. And so the existing results, if you require that that the compaction algorithm is stable, there's a lower bound of n log n. But if you remove that requirement, it's been improved to n log n, and then most recently to big O of n. This result is deterministic and gives the first asymptotically optimal ORAM construction with big O log n overhead. And what we do is we give another big O of n algorithm that improves the constant to about 23,000. At a very high level, the way you can think about this is that we started with the ORAM paper and we asked ourselves, if you remove the requirement that this algorithm needs to be deterministic, and then you start paying attention to constants, how much can you change about the algorithm in order to make it a lot faster, and how fast can you get? Unfortunately, 23,000 n is still not exactly fast, but it's at least faster. Here's sort of some comparisons between the two algorithms. Note that the 2 to the 111n runtime there at the bottom for Optorama is not from their paper themselves. They weren't interested in constants. But if you sort of follow their construction, you get a sort of estimate of at least that large of a runtime based on the kinds of expander graphs that you need to get the construction to work and what kind of expander graphs are known to exist. And the other sort of comparisons I'll comment on as I go through the proof by picture here. So as a warm-up, if the easiest way to do this is just to grab random things and swap them if they're out of place. So just grab something from the left and something from the right, and if it's red on the left and blue on the right, swap. If you get both blue or both red, or blue on the left and red on the right, you don't touch it. It's really easy to find a swap at first, and then as you get close to the end, it takes n squared over 4 times even to find the last out of place swap, just working randomly. So it's big O of n to reduce the density of out of place balls to some constant, but n squared to finish. So here is just a picture of the idea of getting blue on the left and red on the right by random swaps. And to improve this runtime, we divide it into 4 segments: blue, red, purple, red, and red. And by doing random swaps between the purplish blue and the purplish red, you can keep the density of both the purplish sections near 1/2, and then swap blue with purple and then red with purple to get very blue and very red elements on the side. To get an idea of why this is helpful, you can look at these. So the time it takes to push the density below some bound of the top picture is integral of 1 over rho squared, if rho naught is your target density. This is because it takes about, if the density is rho, it takes 1 over rho time to find something out of place on the left and 1 over rho time to find something on the right, and these are independent guesses. On the bottom, if you keep the density of the purplish red section near alpha, you've replaced one of the rho terms but with alpha, and so now you've dropped from basically 1 over rho to log rho in your cost. So this can be just sort of thought of as a trick, but I think it's a fun trick for sort of controlling that you only need to tighten up the density in part of your array. So once you have that as a gadget, what you do is you compact the really red or the really blue areas, and then you readjust your boundaries and keep going down and down until you get it as compact as you need to be, omitting some details. The next sort of trick I want to say here is that I mentioned earlier that it's worth thinking about how you would do this algorithm if you had unlimited client memory. You can do this if you shove things down into very small bins. So if your bin has size log n over log n, then you can store all of the metadata about that bin, meaning the sequence of ones and zeros corresponding to red or blue, in a single memory word. So then you can have the client run on their own local machine whatever algorithm you have for explaining where the compaction, how the compaction should work, and so they can run it sort of locally in their head before they actually interact with the server at all. So skipping the details about Chernoff bounds and keeping track of things that are not, where the densities are a little bit off. So you get your small bin that you can store all the data in a single memory word, and you divide that small bin up into very small bins. And we are going to, so these are constant size bins that we're going to put into a random regular graph. So here is sort of the, and as I said, you can push the edge set into big oval blocks. Here is the sort of big point of comparison between Optorama. So Optorama has a similar situation where you get down to small enough blocks that you can pack all the information to a single memory word. And the way they deal with this is they have a big bipartite graph, and they have, you know, a bipartite graph between their actual data and a huge array filled with dummy elements. And then they conduct this series of rounds where you move red from the top to the bottom whenever you can get away with it and repeat. This is an old, something called self-rooting superconcentrators due to Pippinger. And basically the drawback to this approach is that in order to make it work, you need the expander to have, you know, certain properties that pushes up the constants enormously. So I asked, you know, what if we use a regular graph, a random graph instead of a bipartite graph? What makes this harder about this? So now you just have things in this graph on the right. You have a bunch of arrows, and you have to assign directions to these arrows. So the main problem here is that you could have, with high enough probability that it happens enough that it messes you up, you could have like a tree of depths k for arbitrary k of all red elements. So then you can't easily swap red and blue elements if you have this little like cluster of length of all red. So the answer to this is something called majority bootstrap percolation. So what you want to do is you just want to, so the answer to how you assign the directions on these arrows is you want to assign these arrows so that there are more arrows out than in for every red node. So if there are more arrows out than in, then you can either swap red and blue or red and gray, where gray represents dummy. And then after this, every node will have, you know, begins with, so you move at least one element out of every red bin. So now every element will have at most D instead of D+1 red elements, and then you get this D over D+1 loose compaction. And how do you know that you can assign these arrows? The answer is that a greedy algorithm works under certain conditions. So all you do is you scan through the array, and whenever you come to a red element that has a majority of blue neighbors, you point out arrows from that red element to all of its blue neighbors. And when can we do this? You can do this for a Margulis graph or for a random regular graph of degree 13. This is a consequence of the expander mixing lemma. Anyways, so those are just sort of a high level overview of some of the tricks. And just because I think it's fun, you can, here's sort of cramming all of those tricks together onto a single slide. So you have the the density reduction trick to get really small density, and then you go into really small bins where you can get away with using the metadata crammed into a single word, and then you use this majority bootstrap percolation. And I will stop there. Thank you for your attention.
Thank you very much, Samuel. I don't see any questions in the Q&A. Anyone from the panelists? All right, so I would like to ask, first you mentioned that your algorithm is probabilistic while ORAM is deterministic. So do you allow some failure probability?
Right, yeah, so we just have to keep the failure probability negligible in the array size.
Mm-hmm. And also, if you consider parallelism, then what would be your depth of the algorithm?
Well, we weren't optimizing for parallelism, but so I think the depth is it might still be. I think it's like log n, but I would have to actually check on that and get back to you to be sure offline.
All right. So thank you again, Samuel.
Thank you.
And we'll move to the next talk by Paul. So Paul, are you ready?
Yep, can you see my screen?
Yes, great. So the next talk would be efficient three-party distributed ORAM by Paul Bunn.
Great, thanks. Yeah, so this is joint work with Jonathan Katz, Eyal Kushelevitz, and Raphael Ostrovsky. Not sure, somehow I lost pointer control. So in this work, we do two new things. We introduce a three-party distributed point function protocol and a three-party ORAM protocol. I'll revisit the slide again after I've defined what these two notions are. So first, a distributed point function falls under a broader class of problems introduced in 2015 by Goyal and Shai of function secret sharing. So function secret sharing is an extension of ordinary secret sharing, where one party who knows the secret, and on the picture on the left, just a number, splits it amongst some set of parties, in this case two, such that any party by itself can't reconstruct the secret, but if they get together, they could recombine the shares. So in function secret sharing, it's the same idea, but instead of splitting just a number, now you have some function in a class of functions that you're sharing between some number of parties. Again, with the same property that some subset of parties cannot reconstruct the function. But if you have enough of the parties, for example, all of them, they can reconstruct the full function. So concretely, a function secret sharing scheme has three protocols. There's a dealer who knows the function and distributes some compact representation of that function called keys to each of the parties. So that's the gen protocol. There's an eval protocol where each of the parties, given their key share and some public input evaluation point X, they are able to compute their share of the output of the function on that input. And then there's a reconstruct protocol, which takes some subset of the party shares, typically all of them, of the outputs, and combines them in some way to get the actual f of x. Usually eval in practice is just a XOR recombination of the shares, but that's not necessarily the case. So as I mentioned, the subclass of functions that we're going to be interested in are called are point functions, or distributed point functions in the case of FSS. So in this setting, you have a point function is pictured here on the lower right. You have a domain and some secret value of that domain, I, where the function is 0 everywhere except at that point. And at that point, it has some value v in the range of values. And both I and v define explicitly what the function is, the point function, and that is what must be kept secret from all the parties. So we create a 3-party distributed point function protocol. It's secure against 2 semi-honest corruptions. It just uses as a cryptographic assumption a PRG. One of the main points that are interesting for people to try to optimize in FSS in general, and certainly in DPF, is how expensive the GEN protocol is in terms of dealing keys to the different parties. So the best known results for DPF are root N communication, and our results asymptotically match this, but some advantages of ours, we have some concrete efficiency gains if you look at the constants, and also the protocol is simpler to use, and this will become relevant, and we'll have a demonstration of this in our next result. So I'm not going to get into the specifics of the 3-party DPF protocol that we come up with, so I'm happy to answer questions about it or refer you to the paper or the slides. So the next result that I want to talk about is related to ORAM, and it builds on the DPF as a building block. So I just want to back up and give some context on, in general, how DPF is related to ORAM. And so there's, as was made in the original DPF paper in 2015, DPF can give you directly a PIR. So imagine in this case, this is a 2-party DPF scheme. So your client, the dealer, is on the left here, and he wants to access position I from a 2-server database. Both servers hold identical shares of the database. So what this client would do is he would generate a DPF function that is 0 everywhere except for 1 in the ith position, and he would use the DPF scheme to deal keys for this to the 2 servers. The 2 servers would evaluate those keys at every single index of the domain. Here the domain size is however many elements are in the database. And so this is depicted, the top database, his shares of every evaluation point are the A's, and the second server shares are all the B's. And DPF gives you the property that if they were to XOR their shares, it would be 0 everywhere except for a 1 in the ith position. And now each database can perform a dot product with their share of the DPF function times the corresponding element of the database, and send the result of that dot product back to the client. And the client can just XOR these shares together, and you'll have the property that there's cancellation everywhere except for in the ith component. So that's how DPF can give you PIR. Conversely, DPF can also give you private information writing. In this case, I'll just show an update as opposed to a write, but a write you can get from an update by first doing a read and then updating by the XOR value of the read followed by whatever you want to write. So it's a similar setting. In this case, I'll show a 2-party construction again, but there's one key difference here. But so in this case, the client now again, he has a secret index that he wants to write to and a value v that he's going to update the databases by. So again, he generates a DPF for the scheme, and you have the same setting above. The one thing I will mention is that the databases here, for PIR, they were identical. The two servers had identical databases. In this case, the two databases are different. So they XOR, they're an XOR sharing of the actual database. So neither database server has the data in the clear, or the actual data encrypted, or what have you. But now they each have shares of the data, and that'll be an important distinction. But anyway, for the DPF's perspective, the client deals keys for this DPF function, the same property. Each server evaluates at every possible point. And the property is that if they were to XOR their shares, it would be 0 everywhere except for a V in the position I. And now instead of doing a dot product, each database server just directly adds or XORs their evaluation point into their database. And now both databases will have been updated, and if you look at those updates, they will cancel everywhere except in the key position I, where they've been updated by the update value V. So ORAM is just a combination of PIR and PIW for the most part. So DPF can be used to give you ORAM. Our result is about distributed ORAM, which is similar to ORAM, but with a little twist in that now you don't have a client anymore who's allowed to explicitly know either the read position or the read value, or the write position or the write value. Instead, you want to distribute the client among some set of parties. And just as a side note, distributed ORAM is not the same thing as multi-server ORAM. In multi-server ORAM, you attempt to solve the ORAM problem using multiple servers, but you still have typically a single client that knows the read and write positions and values. And so DORAM is motivated by MPC in the RAM model of computation, where now you want a collection of parties performing MPC, and each one is not allowed to know the actual operations. So we obfuscate that information from these parties by distributing the client and then running the underlying ORAM protocol. So going from ORAM to DORAM, you can do just a generic transformation using generic MPC, and this has been done before. And in practice, it's not as efficient, potentially if you have a direct protocol, which is what we build. The other thing that I'll note here is that in an earlier DORAM work by Donor and Shalat in 2017, they noticed that building DORAM from FFSS and specifically DPF asymptotically, if you look at the computation, you can have worse results. But in practice, because the constants are much smaller and because the computation is local and simple, like XORs, it actually can be faster and open up DORAM, on a realm of database sizes that were previously inaccessible, even by asymptotically superior constructions. So our second result, we use this generic transformation of DPF into ORAM in the three-party case, and we build the distributed client based directly on our three-party DPF protocol, and from that we get a three-party DORAM protocol. So if you notice, the top protocol was secure against 2 semi-honest corruptions. The bottom protocol is a three-party protocol, but you lose tolerance to 1 corruption, so you just get 1 security. It's still root-end communication, but now you have linear computation, and again, as noted by Donor and Shalat, this oftentimes means a concretely faster protocol, and this is something we're working on actually benchmarking. Yeah, that's all the content. Any questions?
Thank you, Paul. I don't see any questions in the Q&A. Anyone from the panelists? So one question, is it specific to 3 parties, or your construction can be generalized to more parties easily? I mean, like,
Yeah, so there are 2 results. So there's the DPF and the ORAM. For the distributed point function, it concretely is, you know, too secure for 3 parties. Extending it to more parties, if you want the same, if you just want like 2 out of n, then you can trivially extend it to more parties. If you want n-1 out of n security, then it is not extensible in that way. And in fact, if you look at the original FSS constructions, they talk about generalizing to higher numbers of parties and higher thresholds, and they have generic results for the you know, for the asymptotic costs. They're not lower bounds or upper bounds, but yeah, the underlying protocol is not directly extensible to a higher number of parties. It's specific to the 3-party setting, which means then the ORAM result is as well.
Mm-hmm. All right. And one more thing, could you elaborate a little bit more about the difference between distributed ORAM and multi-server ORAM?
Yeah, so in multi-server ORAM, you have a client that knows what position he wants to read or write to. He knows the value that will be read, or, you know, that gets read, or that he wants to write. And the multi-part is just for the concrete protocol of how you actually do ORAM in the setting, and it means that the memory of the database is distributed amongst multiple servers in some way. And you can get efficiency gains if you consider multi-server ORAM as opposed to single server ORAM. In the distributed ORAM setting, it doesn't make a statement about the number of servers. Typically, the number of servers is the same as how you partition and distribute the client. That's not necessarily the case. The distributed part is just referring to the client, and now it's saying instead of having a single client, we're going to simulate the client with 2 or more parties, and those parties are not supposed to be privy to the information of which position I is being read or written to and the value that gets read or written.
Mm-hmm.
And typically when you use an MPC, you use the same set of parties to distribute the client as you use for the servers that are storing the data. But that's not, you know, implicit. That's not explicit in the definition. That's just typically how it's used.
Right, got it. Thank you. Anyone else? All right, so thank you, Paul, and thank again to all the speakers, and this will be the end of this session.
Thank you.
Okay, thank everybody. Is Vladimir around?
Hi, Clemente, yeah.
Okay, so this was the last talk in the conference. Do you want to say something?
Yeah, I didn't really prepare anything because everything I wanted to say, the nostalgia for the actual real meeting in Amalfi, I said in the beginning. I can repeat some of the main thesis here is that I really wish we were right now in Amalfi and seeing each other, and you know, the beautiful Italy, the food, the sea. Hopefully next time. The conference, I think in the end, it went really well. The talks, everything was on time. The talk, nobody got missed out. All the talks, you know, all the speakers appeared, and all the presentations were very clean and to the point, which is I really like this this format. So anybody can much easier has much easier time navigating what this conference is about, watching this 5-10 minute presentations, and then deciding if they want to see the full talk and or read the paper. So that's I think that's great. And I wanted to thank everybody, Clemente, the general chair, the speakers, the program committee, the external reviewers, people who came to watch the talks. Thank you very much. It was great. I think that's all I wanted to say. Now we have half an hour or so that we planned to socialize. But also Clemente maybe wants to say something, then we stop the recording and, you know, have some small talk.
Okay, so first of all,